the basic equation for fin, which is actually the fin equation. So in that case, we actually assumed a fin of any cross section, and we said that the basic idea is that whatever heat coming in, some amount is actually convected out, and some amount is actually conducted again to the in the x direction. So we said that for last class, okay, that is fine. Now we are actually going to simplify our condition by uh, going with the fin of uniform cross section. In that case, we can actually reduce our equation to a very simple homogeneous partial differential equation, the ordinary differential equation, t square theta by dx square minus m square theta, where theta we actually wrote as 3 minus t infinity, because t infinity is actually same everywhere. And m square, it is actually given as hp by kac. We are actually given m square because in the solution it is actually coming as m. So that means every time we have to write root of hp by kac, root of hp by kac. It's actually a bit uh, problematic to say. So in order to make everything simple, we just call m square as hp by kac, where m is actually the fin parameter. And we said that the basic equation or the solution is we can actually write as theta x. That means how the temperature is actually varying along the length. So T minus T infinity is actually varying along the length of fin. And we said that T infinity is actually constant. So it is basically theta is basically how the Ts is actually varying along the length, fin length. We actually got the solution a into e raised to mx plus b into e raised to minus mx. We can also write it as cos hmx and sin hmx. So we said that in order to solve that, two basic boundary conditions required. One is actually at the base. So one is actually at the base at x is equal to 0. We are actually saying T is equal to Tb, the base temperature. So in many cases, base temperature is actually same as that of the surface temperature. So it is actually easy for us to understand. So therefore, we can actually say the one condition, boundary condition, at t is x is equal to 0, we have theta b. So the other condition, which is actually at the tip, we can actually have four different conditions. One is actually the prescribed temperature, okay, and one is actually the convective condition, convective heat transfer. Another one is adiabatic tip, and last one is actually the infinitely long fin. Okay, based on these four conditions, we actually saw how the temperature is actually varying along the length, and what is actually the total heat flux, or what is actually the total heat that is actually transferred from the fin into the ambient condition. Okay, yeah. So that's where we were actually seeing. So that means with if you are actually attaching a fin, you're actually attaching a fin like this. What is actually the total heat transferred to the fin directly from this equation? Okay. For example, if this is actually for this uh, prescribed temperature. Okay. So again, one more time, m which is equal to root of hp kac theta b. Okay, if it is a convective heat transfer, we saw what is actually the temperature as well as what is actually the total heat transfer. So all those things we have actually seen. Okay. Yeah. Till now, everything is actually fine. We got some understanding of what are actually how the temperature variations are actually happening. So all those things are actually there. So now we are actually going to see some parameters which actually tells us whether we should actually go for fin or not. Okay. So we might actually think that every time when we are actually going to increase give a fin, then the efficiency or the heat transfer is actually going to increase. But think of this case: if we are actually going to have a yeah, if you are actually going to have a fin like this, okay, suppose the surface material is actually of I don't know, maybe conductivity of K1, and this material is actually of conductivity of K2. Okay, so if you are actually doing like that, then you can, if K1 is actually greater than K2, K1 is actually going to be greater than K2, then here you can actually see that this is actually going to be an this fin, it is actually going to be act like a resistance, okay, or it is actually going to hinder this because the conductivity of fin is actually lower than that of conductivity of the material. Okay, so therefore, if the fin was actually not there, then more heat would have been actually transferred. So that condition is actually there. Another condition is that suppose if you are actually putting a long fin, okay, I don't know how long we will actually see. If we are actually putting a long fin, okay, suppose the heat transferred through this fin is we can actually say Q1. Okay, so heat transfer through this fin is actually say Q1, and maybe we have actually spent say some 10,000 rupees. Okay, we have actually spent some 10,000 rupees for making this fin and all. Okay, so now with the 10,000 rupees, if we are since we are actually spending that, we can actually see that using a fin we can actually give out some Q1 amount of. But if you are actually reducing the fin by maybe a little bit size, the same material, everything is actually there. Only we are actually reducing the length a little bit. Okay. So in order to that, we are actually reducing the length by say half. So in that case, we can actually say instead of 10,000, we are actually going for 5,000. Okay. And obviously the heat transfer will be actually going to be less, which is actually Q2. But if Q2 by Q1, if you're actually saying almost 90%, so Q2 is actually 90% as that of Q1, okay, then you can actually see that instead of spending 5,000 more, with the spending 5,000 more, I'm just making some 10% increase in Q1 only. It's 10% increase in the heat transfer rule. Okay? So all those things we can actually see means in order to understand what is actually this length and how effective is this. Okay, so whether heat transfer is actually increasing, and even if it is actually increasing above what increase, we can actually justify the use of fins. So those things also we have to actually see. Otherwise, it is actually going to be incomplete. Okay, so yeah, it is good that we have actually now have the idea of the temperature variations as well as the heat transfer, etc. But we must actually justify for using this fits. That is actually the part of engineering, right? So that's what we are actually going to see in this class. So for that, two parameters are actually there. First is actually fin efficiency, and second one is actually fin effectiveness. Okay. Yeah. First, we will actually see for a single fin what is this efficiency and effectiveness. Then we will actually see for a row of fins or a multiple fins what is again this effectiveness, efficiency, and all those things. Okay. Yeah. So this is what we are actually going to see. Fin efficiency. Fin efficiency is what we are actually going to see. Okay. Fin efficiency. The fin efficiency, as the name suggests, it is actually going to tell us, okay, the fin efficiency from the derivation itself we can actually see that it is actually the heat transferred through the fin, okay, so divided by fin maximum heat that is actually possible. Okay, so we can actually write as uh, is equal to Q heat transferred from the fin. Okay, the Q from fin maximum. Yeah. So here is okay. So Q transferred to ambient through fin divided by maximum possible heat that can be transferred to ambient. Okay, the heat transferred to ambient through fin divided by maximum possible heat that can be transferred to ambient through fin. So that is actually the definition of fin efficiency we can actually see. Okay. What is actually heat transferred to ambient through fin? Do we know that? Do you know what is actually the heat transferred to the fin? Heat transferred to ambient through fin. Do we know that? Do we know what is actually the heat transferred to the ambient through the fin? Can you all hear me?
Yes, sir, we know that.
Yeah, I just need some response. Otherwise, I feel like no. Okay, so we know that heat transferred to ambient through fin. but we are actually not but we don't know what is actually the maximum possible heat that can be actually transferred. Okay, so for that we are actually yeah, so what is actually the condition in which maximum possible fin is actually going to be there? So that's what we are actually going to see. So what we are actually saying is the temperature difference, the temperature difference which is actually causing the heat transfer, uh, the maximum temperature difference, I'm sorry, the maximum temperature difference. Yeah. So before writing, we can say that we are actually saying Q is equal to HA delta T, right? Or we can actually say theta. Theta is equal to T minus T infinity. So what is actually the maximum condition of T minus T infinity? Okay. So where is actually going to be this temperature is actually going to be maximum? It is always going to be maximum at the base, because we know that as the length increases, the temperature is actually decreasing. Okay, so the Q is actually going to be HA theta. Okay, so H is actually constant. We know the area of the fin is actually going to be constant. We know. Okay, so area of the fin, that is also going to be constant. Whatever the area of the fin. What I'm saying is H A fin into theta. That is actually the heat transferred from fin to the ambient, right? So what I'm actually saying is, in order to make it to maximum, we cannot change H, okay? And we cannot actually change AF also for a particular fin we are actually talking about. Okay. So what we are actually saying is, the maximum heat transfer is actually possible if the full length of the fin is at temperature TB, because TB is actually the maximum temperature. TB is actually the maximum temperature possible in the fin. So if you can actually somehow make the fin such that the wall fin is at a temperature TB, then the heat transfer to the ambient is going to be maximum. Okay, so that's what the maximum heat that can be actually transferred to the ambient. Okay, yeah. So that's what we are actually saying. The maximum temperature difference, maximum temperature difference maximum temperature difference causing convection is theta b. Okay, so TB minus T infinity. So this actually happens if you are actually having this uh, yeah, and this happens when, at what when will this happen? This is actually the conduction we are talking about, right? The conduction talking about is actually yeah. So when the conduction resistance is actually going to be minimum, or when it is actually going to be almost zero, then we are actually going to have temperature throughout, same temperature throughout. Are you understanding?
Yes, sir.
Yeah. So this happens when, when R conduction tends to zero, or in other way we can actually say that K tends to infinity, right? So if you are actually having a material of infinite conductivity, then everywhere the wall surface we are actually going to get the same temperature, which is actually same as that of the base temperature. Okay. So therefore we can say that at this condition Q max occurs. Okay, so Q max occurs. So whereas Q fin max, so therefore we can actually write as H A theta B. So A fin we can actually write. Okay. H A fin theta B. So in that condition, we can actually see that the um, yeah. So we can actually see that the heat transfer is actually going to be maximum. Okay. So were we actually using AS or AF for the surface area? I think we were actually using AS only. Yeah. A surface area. HAS theta B is actually the total heat transfer. Okay. So therefore, we can actually rearrange our efficiency such that Is that yeah, it is equal to, as we said, q fin divided by q fin max. So again, on the top, we can actually see that what is actually the actual heat transfer from fin, actual heat transfer from fin, okay, divided by from fin divided by. Is that actually possible that the wall surface should be at the same temperature? It is actually an ideal condition. So none of the material will be having a infinite thermal conductivity. So therefore, that is actually an ideal condition in which the wall surface or the wall fin is actually at the same temperature. Okay? So therefore, we can actually write that the ideal heat transfer, ideal heat transfer from fin, if entire fin were at base temperature. Okay, so that is actually this. We can actually say the efficiency of the fin. An actual condition divided by ideal condition where if the fin were actually of the same temperature throughout. Yeah. So now, what is actually now we can actually see what is actually the efficiency for each and every condition. Like we can actually see what is actually the efficiency for prescribed temperature. We can actually see what is actually the efficiency for convective, adiabatic, long fin. All those conditions we can actually see now. Okay. So anyway, for simplicity, we are actually seeing only for simple cases for adiabatic condition, adiabatic tip condition. Can anyone say what is actually the efficiency? Eta fin is equal to q fin divided by q fin max. So what is actually the q fin through adiabatic tip? Can anyone tell me? Or should I take
M 10H ml.
m tan h ml into theta b, right?
Yes, sir.
Yeah, very good. Thank you. So, what is actually the Q fin max? It is equal to H AS theta. Okay, so that is actually this formalized. But we actually know that M is equal to root of HPKAC. Okay, and uh, AS. What is actually surface area? What is actually surface area? Surface area is equal to perimeter into length, right? Surface area is equal to perimeter into length. So therefore, we can actually write as we are actually going to cancel these things. So M we are actually writing as HP by KAC. So H and P are actually there in the denominator also. Okay. So HAC we can actually write as H into P into L. So on the numerator also we are having HPKAC. So if you are actually doing that, what we are actually getting is 1 by L. So L from this, and then we are actually going to get KAC by PL, KAC by PL into tan H ml. Okay. So, but what is actually this KAC by not PL, HP? Okay. KAC by HP. Sorry, HP. But we know that HP by KAC is equal to N. Okay. So therefore, we can actually write as tan H ml divided by ml. Okay. So numbering. So this is actually given as 47, and this is actually given as 48. Okay. So this is actually the efficiency of the of an adiabatic condition. Tan HML divided by ML. Okay, we will see the significance of why the efficiency, etc. later. But this is what the efficiency is actually going to be. So we can actually see that with L increasing, the tan HML is increasing as well as ML is also increasing. Okay. So we can see that as the L increases, we don't know whether the efficiency is actually going to increase or decrease because both tan HML as well as ML is actually going to be increasing. Let's see, we will actually see that later. Okay. So likewise, we can actually find for long fin also. For a long fin efficiency, we can actually call it as adiabatic fin, and we can actually call this as long fin. Efficiency of long fin again Q fin by Q fin max. Okay. What is actually the heat transfer for a long fin? It is going to be HPKAC. So that means M into, in that case there is no tan HMR. So into directly theta B divided by H AS into theta B. So theta B cancel. AS again is equal to P into L. So if you are actually going to do that, what you are actually going to get is 1 by ML. Okay, so that is actually the efficiency for long fin, or efficiency for the long fin. So we have actually seen now what is actually the efficiency for adiabatic tip condition as well as efficiency for a long fin. Okay. So, but mostly what is actually more important from our perspective is actually the convective heat transfer condition. And that is actually the more appropriate or more common. Okay. But for the convective, again, we know that the equations corresponding to the convective was actually very complicated, right? It was actually very complicated. Obviously, you can actually use that. There is no restriction in that. You can actually see Q of is actually there divided by HAF delta or HAS theta B. That is actually going to give us what is actually the maximum. So ratio of that will obviously going to give what is actually the efficiency. Okay. So, but what I'm actually going to show is actually a little bit more easier one or a tricky one. So in that case, what we are actually going to do is, so instead of having the full length for the convective, okay, so this is actually the convective fin we are actually seeing. Okay, so here we are having theta B, okay, and here we are having theta L. Some temperature is actually there, and from here also we are actually seeing heat is actually going to be transferred outside. Okay, so H tip is actually there as well as H and T infinity is actually going to be here. Okay. So in this case, if we are actually assuming H tip is equal to H itself, so the tip heat transfer coefficient is actually same as H. Okay. So what we are actually trying to see is, so here from the surface through here perpendicular to this, so some amount of heat is actually being transferred. I don't know, maybe q amount of heat is actually being transferred, and from the tip we are actually going to say q tip is actually going to be transferred. So now listen carefully, what I am actually going to say is, so this q from surface we are actually saying q from surface, it is actually happening over here through over a length of L. So we are actually saying the it is actually having a length of L. Okay. So now what I am actually going to do is, so here I am actually going to have a fin which is actually of length bit more, L plus LC. Okay. So or we can actually say simply LC we can actually call. Yeah, I am actually calling it as LC. And I am actually going to give this tip an adiabatic condition. Okay. I'm actually going to give this tip an adiabatic condition. So I made this length LC such that the heat transfer from the fin is actually going to be Q is equal to Q surface plus Q tip. Understand? So therefore, what we are actually seeing is we have actually given a correct length instead of a actual length. we are just assume the fin is actually of a corrected length, okay, such that total heat transfer from the fin is actually going to be same. But for the longer one, we can see that we have actually put an adiabatic condition. Okay. So if therefore uh, the easiness what is actually that. So here for the condition one, we have to actually use in order to find what is actually the q, we have to actually use the equation given by the convective heat transfer condition. Okay. It's actually a bit complicated, but it is not that complicated. You can actually use that. Okay. But it is actually a bit complicated compared to adiabatic filtering. Okay. So, but in case of condition two, what we can actually do that. So I am actually assuming this convective condition to that of an adiabatic condition, but with a length LC. Okay. So therefore, you can actually use the same equation that of an adiabatic condition. Q is equal to m into tan HM LC theta b. Okay. So if you are actually doing that, then Q2, this is actually Q2. Okay. So here Q1, the total. So here you can actually say that Q1 is equal to Q2. Okay. So the total heat transfer is actually going to be same, but we have actually reduced our analysis. Okay. So now we are actually having a very simple equation in hand. Okay. So that method, so this is actually one method in which you can actually use for the analysis of convective heat transfer. Okay. It doesn't actually matter. So because the total heat transfer is actually going to be same, because that's what we are actually more interested in. Obviously, the temperature variation might be actually a bit different than those. Okay. But the total heat transfer is actually going to be same. That's what we are actually more interested. Okay. So that condition, yeah. So this length, we need to actually, we must actually know how this length is actually going to be. It is actually very simple formula only, but this method is actually known as the corrected length method. Okay. So therefore, that's what we are actually going to see. Corrected fin length. Corrected fin length. So this is just a side topic. Okay. So here, what we are actually saying is we are actually reducing we are actually correcting the length such that the same heat is actually going to be transferred for a convective fin as well as that of an adiabatic fin. Okay. So we are actually writing fin with the convective fin with convective heat transfer at tip can be considered as can be considered as fin with adiabatic tip by replacing the actual length with a actual length with corrected length. Corrected length. Okay. So, but the corrected length, we are actually assuming the equivalence of heat transfer between two conditions. Okay. Yeah. So the correction in length, correction in length is based on assuming equivalence between heat transfer from actual fin with tip convection and actual fin with tip convection and hypothetical fin with adiabatic tip. Okay, so that is actually the condition. So corrected length for fin, length, we can actually call it as LC is equal to L plus AC by P. Okay, so where AC is actually the yeah, AC is cross sectional area, is cross sectional area, cross sectional area, and P is perimeter of fin at tip, perimeter of fin at tip. Okay, so therefore, yeah, so that is actually the corrected length and corrected length and actual length. If this is actually the actual length, okay, so we are actually calling it as L. Okay, it is actually L, and here we are actually having a Q convection. Okay, so Q convection we are actually going to have, and in the corrected length we are actually going to have a longer one. Okay, so longer one we can actually say so this is actually L, this is actually L, and this is actually LC. Okay. And therefore this much length it is actually going to be AC by P. Okay. In this case we are actually going to have the adiabatic tip. So this is adiabatic tip. So this is actually the equivalence for that. So for rectangular fins, from this a cross sectional area divided by perimeter we can actually calculate for rectangular fin, basically it is actually taken as L plus T by 2. LC is equal to L by T by 2. For a cylindrical fin, okay, so LC is equal to L plus D by 4, where D is actually the diameter of the system. Okay. So, but the beauty is that therefore we can actually see that efficiency for a convection fin, okay, so convective fin, how we can actually write for adiabatic fin, we actually wrote tan H ml divided by ml. So here instead of ml, we have to actually write mlc. Okay. So now the convective or the efficiency of a convective fin, we can very easily write as in terms of the adiabatic condition. Okay. So that is actually the basis for this corrected length. Okay. Yeah. So now the efficiency of the fin, why it is actually very much important, or why we are actually using it for the further analysis, it is actually very easy to use. Okay? For example, if we are actually going to use, or if we are actually going for some analysis and all, there is actually some there will be actually some conditions where for a particular kind of, for a particular material with a for a fin of particular material for a particular length and all, there we can actually have from there directly what is actually the efficiency of the system. Okay, so if we can actually find, or from some data table, if we are actually getting the efficiency of a system, for example the convective fin. Okay, if you are actually directly having the efficiency of a system, then we can actually find Q fin. Q fin we can actually directly by multiplying with eta into mls. Okay, so that is actually the benefit of finding, or what is that is actually the benefit of efficiency of system. So in many of the calculations, the overall calculations are actually going to be simplified. Okay, so that we will actually see in the next topic, which is actually the fin effectiveness. So now we have actually seen fin efficiency, which is actually an important parameter from a fin point of view. Next one is actually the fin effectiveness. Okay, we can call it as fin effectiveness. Fin effectiveness. Okay. Fin efficiency means how good the fin is actually going to be performing based on the maximum value. Okay, so that's what this sorry, so that's what this fin efficiency or is actually going to be talked about. Okay, how means what is actually the efficiency compared to the maximum condition it can actually do. But fin effectiveness is actually something different. Okay. Uh, so as we said, so as we said, uh, we were actually saying if we are actually having this kind of fin, uh, it is actually giving some amount of heat. Okay, it is actually giving some amount of heat. I don't know QF. But what we are actually saying is, if fin was actually not there, if the fin was actually not there, then heat would have been actually still transferred from this base area. Okay? So by attaching the fin, we are actually increasing the surface area, right? Total area is equal to a fin. Okay? But if a fin was actually not there, a no fin condition, that means the surface area is actually going to be same as that of the base area or the cross sectional area for a constant area. Okay. From here itself, still the heat would be actually goes out. So if you are actually comparing these two, if yeah, by comparing these two, we can actually see how effectively fin is actually transferring the heat. Okay, so that is actually known as fin effectiveness. Okay, so we can actually call it as fin effectiveness. Fin effectiveness is defined as effectiveness is defined as ratio of the fin heat transfer rate fin heat transfer rate to the heat transfer rate heat transfer rate that would that would exist that would exist without fin okay? So that is actually the heat transfer rate with and without fin, the ratio for that. Okay? So therefore we can actually write effectiveness, it is actually given by epsilon. Effectiveness fin is equal to Q fin divided by Q no fin. Q fin divided by Q no fin. So Q fin, we know from our equation. If fin was actually not there, then what would happen? H into AB. AB is actually the area to which the fin was actually attached. Okay, into TB minus T infinity or theta B. Okay, so that is actually our yeah, H into AB into TB minus T infinity. Okay. So in this condition, we are actually assuming it for a, if we are actually assuming it for the same condition of also for cross-sectional area, then we can actually say that the area is actually going to be same throughout. Okay. So we can actually say that if effectiveness of fin is actually less than 1, so that means fin acts as insulation. Right? So effectiveness less than 1 means what? By attaching the fin, we are actually reducing the total heat transfer. Okay? That is actually not at all beneficial. That is actually not at all beneficial. So if we are actually talking about cooling, yeah, there is actually some cases where it might be actually required. So, but as a fin purpose itself is actually going to increase the. So therefore, if we are actually having effectiveness less than 1, that means fin acts as an insulation. The effectiveness 1 is equal to 1 implies, okay, so addition of fin has actually no benefit. Addition of fin has no effect, okay, has no effect or benefit. Because with and without fin, we are actually going to get the same. So if the effectiveness is actually going to be greater than 1, obviously heat transfer enhanced. Heat transfer enhanced. Okay, but as we said, maybe if you are actually giving a small, so suppose if you are actually getting an effectiveness of 1.2 or something, and for that we need to actually make some yeah, obviously we have to actually manufacture the fin, and we have to actually attach the fin either as a integral part or as actually an addition. So we need to actually attach it, and we have to actually do it even if effectiveness is actually going to be 1.5 and all. We would actually say that there is actually no benefit in adding, being keeping in mind what are actually the trouble we have to actually go through. Okay, so basically we are actually saying the fin can be actually used if the effectiveness is actually going to be greater than 2, but that is actually not a rule or something, but basically this is what we actually do. If the fin is actually not giving more than 2 times the heat transfer without the fin, then there is actually no point in adding that. Okay, so we can actually say that use of fin justified if effectiveness of fin is actually going to be greater than 2. But again, that is not a hardcore rule or something. Okay, so in some cases maybe we can actually say it is justified only if effectiveness is actually going to be greater than 3 or something, because if you are actually going for a very highly costly materials and all, and if it is actually going to give even 2 or 2.5, you will actually say I don't want that. There is actually no benefit in putting that much money into that. Okay, and also the trouble whatever we have to actually go through. Okay, so again we are actually going to see for adiabatic fin. So adiabatic, no, not efficiency, effectiveness for yeah, effectiveness for any fin, we actually said q fin divided by h ab into tb minus t infinity. Okay, so that's what we actually said. Okay, but what is actually the q for any fin? Q for any fin, obviously we actually we have the equations, basic equations. Okay, but here a simple one we have just discussed, which is actually efficiency of a fin into h into a fin into tb minus t infinity. Okay, so therefore divided by h into ab into tb minus t infinity. Okay. So we can actually cancel these. So therefore we can actually write efficiency of fin into area of fin. Area of fin means area of surface area. It is right. AS divided by AB. Okay. Area of fin we can actually write as AS. AS by AB. Okay. So that is actually the effectiveness of fin. Okay. So here, yeah, so that is actually what this effectiveness of fin is. For example, we can actually yeah, for long fin. Okay, we are actually saying for long fin, if you are actually taking effectiveness is equal to root of HPKAC into TB minus T infinity divided by H into AB into TB minus T infinity. Okay, so directly we are actually not using this formula for calculation of efficiency of fin. So you can actually see that it is actually going to be uh, yeah, these things we can actually cancel. So in this case, AC is equal to AB, right? AC is equal to AB. So therefore, we can actually write it is equal to KP by HAC. Okay. So that is actually the effectiveness for the yeah, effectiveness for the long fin number. Okay. So that is actually how you are actually calculating. But with this equation, we can actually call it as 50. With equation 50, it is actually the yeah, you can actually have a it can be actually used for any fins and any conditions. Okay. Yeah, from 50 some inferences, from 50 some inferences we can actually get. Okay, some inferences. Okay. Yeah, we can actually call it as 50. Yeah. So here, and also 50.8. Okay, from 50 and 50.8, 50 and 50.8, some inferences we are actually going to get in. Okay. Because we always want to increase the effectiveness. Okay. We always want to increase the effectiveness of the system and load. So how we can actually increase the with an example of long fit, we are actually saying how we can actually increase the effectiveness. Okay. Can anyone give the first point? Can anyone give the first point how the effectiveness can be actually increased for a long fin? Effectiveness is equal to root of HP by KAC. Okay. How this effectiveness can be actually increased? Okay. Yeah. High conductive material we should be having. High conductive material. Okay. It should be having high conductive material. Obviously, as the K increases, you can see that effectiveness increases. Okay. And here you can actually say that P by AC. Okay. Need to be high. Need to be high. Need to be high. Okay, so that means instead of a single fin, suppose if you are having a fin like this, okay, uh, instead of a single fin with the high cross sectional area, here we can actually see that cross sectional area is actually going to be there, and from this perimeter also we can actually find. Okay, so in this case we are actually having perimeter 1 by cross sectional area 1. Instead of a one big fin, here you can actually see some amount of materials we are actually using. Instead of one big fin, what you can actually do is you can actually go for two small fins. So instead of one big fin, you can actually go for two small fins. So here you can actually see that the cross sectional area, maybe if we are actually collecting everything together, maybe we can actually say cross sectional area might be actually same, but we have actually increased the perimeter. Even if cross sectional area is actually same, we can see that we have increased the perimeter so that the effectiveness is actually going to be higher. Okay, need to be higher. So therefore, we can actually see that thin plate fins, thin plate fins. Okay, so these are actually the thin fins. It is actually of very low thickness. Basically, we have actually reduced the cross section area by reducing its thickness. Okay. Thin plate fins, okay, or or slanted slanted pin fins, very small fins, very small fins. We are actually seeing. Okay, slanted pin fins, uh, which are closely placed, can be used. Okay. So basically, instead of using a very high thickness flat plate or a very big cylinder, instead of using very big cylinder, you can actually go for two small slender cylinders. Okay, so which are actually closely placed. So in that case, you can actually increase this HP by AC. Okay. So another important what we are actually getting is as the H increases, if the heat transfer coefficient is actually going to be increasing, then the effectiveness is actually going to be reduced. Okay, so that means the effectiveness of the fin material that is actually more appropriate when we are actually talking about a condition in which the heat transfer coefficients are actually less. Okay. So in a condition where the heat transfer coefficients are actually very high, then there is actually no need for fin. Okay. So therefore, yeah, obviously in some conditions we cannot actually change this heat transfer coefficient. Okay. So therefore, for example, say the heat transfer from a transformer. Okay. So for a heat transfer from a transformer, so on an average, there might be some wind is actually flowing, but in many of the conditions it is actually stationary. So in that case, we can say the heat transfer coefficient vary from say H is equal to 5 or 10 when there is actually no wind or no wind. So that means only the natural convection is actually happening. and it can be actually go up to say 50 or 60 when there is actually wind. There is actually wind. Okay, so therefore in that cases the excess are actually going to be very less. But in some cases where there is actually constantly it is actually having a very high heat transfer coefficients and all, then there is actually no need for this fin at all. So that's what we are actually saying. Okay. So we can actually say fins more effective. Fins are fins are more effective under under lower H conditions. Okay? Heat transfer coefficient conditions. Okay. So these are actually some inferences we can actually get from these equations or from the effectiveness. Okay. Yeah. Yeah. So that's what we can actually see from these fins and fin effectiveness, etc. So now we actually understood why this fin and why it is actually important. Okay. Uh, yeah. So any doubts still here? So now we have actually seen the fin effectiveness and fin efficiency and all those things. So therefore, we actually got some idea where all these fins are actually going to be used at. Okay, but still we are having one problem. So still we are actually not clear on what should be actually the length of the fin. Okay, so whether it should be actually having a 1 meter length or whether it should be actually having a 1 centimeter length. So we are still not sure. So that's what we are actually going to see now. Okay, proper length of fin. Proper length of fin. Okay, proper length of fin. Yeah. So how we are actually going to do is, suppose if we are actually going to have this convective. Okay. So convective boundary condition we are actually going to have to convective boundary condition. So we must actually see what should be actually the proper condition such that we are actually going to get some so such that we are actually going to get the maximum benefit. Okay. So in this case, what is actually the maximum benefit we can actually have? So if we are actually going to have an infinitely long length, okay, obviously if you are actually going to have an infinitely long length, then obviously the temperature is actually continuously reducing, and towards the end we are actually going to have the condition where T is actually going to be equal to T infinity. Okay. So T infinity, why it is so? Because at very low, very high length, all the heat is actually going to be transferred. Okay, the full heat, whatever is actually possible, is actually going to be transferred. 100%. What we can actually say is that 100% heat is actually going to be transferred through these sites. Okay, so maximum possible heat is actually going to be transferred. Yeah. So, so if we can actually compare our condition of convective boundary condition with that of fin, okay, so we can actually compare how much heat is actually going to be transferred with the fin with the convective boundary condition to that of heat transfer from the fin, okay, a long fin. Then we will actually have a comparison. You understand? Because infinitely long fin, that is actually the maximum condition in which heat can be actually transferred. So we are actually comparing with fin with some other fin, what is actually the heat is actually going to be transferred. Okay. By comparing that, we will get an idea what should be the condition such that we will get the long fin. You understand? So long fin is actually the maximum condition in which we can actually go. Obviously, we cannot actually go for infinitely long and all, but mathematically it should be actually infinitely long. But practically, what we can actually say is that at some condition, maybe 1 kilometer, I don't know. After 1 kilometer, we can actually say that it is actually going to be like this, or 1 meter. Okay, some condition we can actually say 1 meter. It is actually going to be the ambient condition. Okay, or maybe in some condition it might be actually 1 centimeter under. Okay, if the Condition is actually, yeah, if it is actually going to be 1 centimeter, at the end of 1 centimeter, it is actually going to have the condition which is actually resembling that of the long fin, infinitely long fin. Okay, how we can actually find that? By comparing these two. Is that clear? Yeah. So we are actually seeing, we
Yes,
are
sir.
actually, yeah, we are actually trying to see at what length this convective heat transfer condition is actually approaching to that of the long fin. So we can actually see to check what length is considered as very long. We are actually trying to see what is actually very long compared to for a convective condition. Very long. Compare heat transfer from a fin of finite length to heat transfer from a infinite length, from a infinite long fin. Okay. So that's where as I said, the importance of this long fin comes into picture, as well as the adiabatic. Adiabatic we have actually seen in the previous class itself. Okay, even though adiabatic is actually something hypothetical, or it is actually not having that much practical importance, we have actually seen by using the adiabatic approximation, we can actually simplify this convective condition. Yeah. So here, what we are actually going to do is we are actually trying to compare the infinite or the fin condition, infinite long fin condition, to that of an adiabatic condition. Okay. So once we have the adiabatic condition, we can actually convert that to the convective condition. Okay. Yeah. So why we are actually interested is because this is how the temperature is actually going to be varied. Okay. So TB. Okay. So this is actually going to be TB, and this is actually going to be an infinite long fin. Okay. T infinity. For an infinite long fin, it is actually hyperbolically, it is actually going to approach the T infinity. Okay. So as the x increases, it is actually going to be hyperbolically or exponentially, it is actually going to be approaching it. Okay. Yeah. So now we are actually going to analyze for an adiabatic fin. For an adiabatic fin, what does the long fin mean? Means what is actually the very long length that can be actually given for an adiabatic fin, such that it is actually going to be approaching that of uh, long fin. Okay, so a fin with an adiabatic tip, at what length we can actually call it as a long fin? For adiabatic uh, fin, for an adiabatic tip fin, for an adiabatic tip fin, we can actually call. So we are actually just comparing Q adiabatic, okay, divided by Q long. What is actually adiabatic? Q adiabatic? Q adiabatic is given by M into tan h ml divided by, for a long fin, it is actually given as M. Okay. So therefore it is equal to tan h ml. Okay. So when can we actually say adiabatic fin approaches the infinite long from this condition? Okay. So adiabatic tip fin approaches infinite length. What is actually the condition? When adiabatic, Q adiabatic divided by Q long is equal to what?
1.
1. Very good. Okay. So we can say that the adiabatic tip fin approaches an infinite length when this ratio is actually going to be 1. Okay, so that means when tan h ml is equal to 1. Okay, yeah. So I'm actually going to give the values for tan h ml. Okay, so here we can actually call it as tan h ml, and this is actually ml. Okay. So obviously, what is actually the maximum value? Maximum value is actually 1. Okay, maximum value is actually 1. And how it is actually varying is actually like this. It is, since it is actually an h value, so it is actually an hyperbolic function. Okay, so actually we can actually see that it actually tends to 1 when ml is actually 5. Okay, so when ml is actually 5, we can actually see that it is actually going to be 1. Okay, so therefore we can actually see that at ml is equal to 5, tan h ml is equal to 1. Okay, so so fin with L is equal to 5 by m can be considered as considered as infinite long. Infinite long. Okay, so this is actually the adiabatic condition we are talking about. For a convective condition, obviously we can actually, instead of regular length, you can actually use the corrected length, and you can actually do the calculations. Okay, so in order to have a adiabatic fin to be actually infinite long, then we can actually go for this equation. Okay, so that is actually the condition in which we can actually have the maximum heat transfer from an adiabatic tip. Okay, yeah. Yeah, so that is actually where you are actually going to get the maximum one. But now, if you are actually seeing, this actually gives us an idea. So here you can actually see it is actually hyperbolic that is actually happening. Okay. So therefore, what I am actually going to do is, I am actually going to see what is actually the value for 2.5. Okay. So this is actually 5 ml. So I am saying this is actually 2.5. If you are actually seeing 2.5, you can actually see that the tan HML, it is almost, okay, it is almost 0.987. Okay, it is almost 0.987. So that means if you are actually having a uh, length of fin of length 2.5 divided by ml 2.5 divided by m, then you are actually going to get 98% heat transfer to that of a long fin. If you are actually having a L is equal to 5 by m, you are actually going to get the maximum fin, I mean maximum possible heat transfer with that particular boundary condition. But even if you are actually reducing the length to half, okay, so now you have actually reduced the length to half, but still you are actually going to get 98% of the previous long length or infinite long fin heat transfer. Okay, so that is actually the benefit. So here now you can actually see that by reducing by almost the length by half, or the material total material now we have actually reduced by half, right? Even if I am actually reducing the total length by half, still I am actually getting 98% of that heat transfer. Okay? So should I actually go for infinite long? I don't have to go for infinite length. Okay, I don't have to go for infinite length. So if your actually consideration is actually the maximum possible heat transfer at any cost, okay, then obviously you can actually go for maximum length or infinite long. But as an engineers, what we are actually interested is actually an optimum conditions. Okay, for an optimum condition, we don't have to actually go for the infinite long. You can actually reduce by half. Okay, you can see that by reducing length by half. Okay, that means L is equal to 2.5 by m. Okay, 2.5 by m. Okay, reduces only 2% or 0.987, right? It is actually 99%, almost 90. So only 1%, only 1% reduces only 1% of heat transfer. Okay, so by reducing this half the length, we have actually reduced only 1% of heat transfer. Okay, again, so therefore we can actually try to reduce again. Instead of 2, I am actually going to take, if I am actually going to take a 2 over here, so here it is actually going to be for 2, it is going to be 0.964. Okay, instead of that, if I am actually going to take 1.5, okay, so if I am actually going to take 1.5, it is going to be 0.905. Okay, so by reducing from 5 meter to 1.5 meter length, suppose if our m is actually comes up to 1, and reducing the length from 5 centimeter to 1.5 centimeter, we have actually reduced only 10%. Okay, if I'm actually still reducing to 1, then I'm actually going to get almost 0.765. Okay, so that means by reducing the length to almost 5 times, we have actually reduced the total heat transfer only by 25%. Okay, yeah. So reduces only the heat transfer by 1% if you are actually reducing by half. Okay, so better to have, better to have ml is equal to 2 to 2.5. Okay, so here what we can actually go for is 2 to 2.5, and obviously we can actually go for, from the effectiveness point of view, we actually saw that multiple fins, that is actually what it's actually, instead of a very big fin, we can actually go for multiple fins. Okay, so better to have ml is equal to 2 to 2.5 and multiple fins, multiple fins. Okay, yeah. So that is actually what we can actually go for. A multiple fins, we have actually studied that based on our effectiveness study. Okay. So now from this length study, we have actually seen that ML is should be actually in the range 2 to 2.5. Okay. So that is actually the condition in which the most economical and where we are actually going to get the most benefit. Okay. Yeah. So any doubts still here? So that actually shows us what that actually ends the analysis for a single fin. So any doubts, anything at all, we can actually discuss. Okay. Yeah. So till now we have actually seen the analysis for single fins and all. Okay. From the analysis, we have actually seen that what is actually the length, and also we actually saw that the multiple fins are actually what required, right? So multiple fins are actually what required. So it is actually important for us to analyze something on this multiple fins also. Okay. So therefore, that's what we are actually going to see now. Uh, yeah. So for multiple fins, we are actually going to have an overall surface efficiency. Overall surface efficiency. Okay. Okay. For surfaces with fins. For surfaces with fins. So that's what we are actually going to see now. So if you are actually going to have a multiple fin, then we are actually going to have this overall fins surface efficiency. Okay. Uh, yeah. So this overall surface efficiency, uh, it actually characterize what should be actually the, if you are actually going to have a particular surface. Okay, if you are actually going to have a particular surface, and if you are actually having a what we can actually say, if you are actually going to have multiple fins, it actually gives us an idea of what should be the fin area and what should be actually the surface area and all. Okay, so it actually gives us an relationship between what should be actually the unfinned area and what should be actually this finned area. Okay, so that is what we are actually going to see. So where the overall surface efficiency eta 0, it is actually given as Qt divided by Q max. Okay. Qt divided by Q max. So where Q max actually we know the yeah, where Qt is actually the total heat transfer, total heat transfer from the total heat transfer from the fin arrangement, okay, divided by maximum possible heat transfer, right? Yeah. So divided by maximum possible heat transfer. So here we can actually say total heat transfer from the fin arrangement, including base surface. Base surface. Okay. So we can actually see it over here. Suppose if you are actually going to have a some surface with the multiple fins. Yeah. So if you are actually going to have multiple fins over here like this. Okay. So this is actually fin 1. Okay. So this is actually fin 1 and this is actually fin 2. So it is actually having some surface area AF. So it is having some surface AF, okay, and it is actually having an efficiency eta F. Okay. So all the fins having the same efficiency, not overall efficiency, the fin efficiency whatever we actually saw. If all the fins are having the same fin efficiency, and if AF is actually the surface area. Okay. And there is actually one more area associated with this, right? Yes, so this is actually the surface. So this is actually the area in which fin is actually not there. So this area, it is actually known as the prime surface. Prime surface. Okay. So this is actually the area or base area to which fin is actually not attached. Okay. And the total area. So here, whatever I'm actually dashing. Okay. So this area, this is actually area to which fin is actually not attached. So that area we can actually call as A unfin. A unfin, to which fin is actually not attached. And fin surface we know AF, including all the surface areas, whatever it is. Okay. So the QT means what is actually the total heat transfer from the arrangement, including the base area. Or we can actually say instead of base area, unfin area. Base unfin area. So base unfin area. Okay. Yeah. Divided by maximum possible. We will see what is actually that maximum possible also. So, but for first, we need to actually see what is actually Qt. That is equal to Q from fin plus Q from unfin. Okay. Q from total heat transfer from the fin plus total heat transfer from the unfin area. Okay. What is actually the Q fin for a single fin? What is actually the heat transfer? We can actually call it as Q fin as eta F into H into area of fin into theta b. Right. So I'm actually interchanging AF and AS. Right? Maybe we can actually restrict here itself. We can actually keep it as AS. AS means the total surface area of the fin. Okay. So that is actually the yeah. So remember, yeah, we just talked about the efficiency, right? Yeah. Where is that? Where did we talk about the efficiency? Yeah. So here, yeah. So from here, from this equation, we can see that eta fin is equal to fin efficiency into Q fin maximum. Maximum we are actually given as H A surface L fin into theta B, right? Yeah. From that we are actually getting it, and we are actually saying there are actually n fins. Okay, so this is actually applicable. This equation is applicable only if the surface area is actually same for all the fins, and the individual fin efficiency is actually same for all the fins. Okay, plus we are actually assuming the same heat transfer coefficient throughout. Okay, from H into A S or A unfin. Okay, A unfin, A unfin into theta B. Okay, so assuming, okay, eta F and AS same for all fins, okay. N is actually the number of fins, okay, yeah, and H is same throughout, okay, yeah. So that is actually the total heat transfer. Yeah. So therefore we can actually see that so where AT is equal to, so this is actually the total heat transfer, uh, yeah, total heat transfer. So AT total area is actually going to be AT is equal to N into N into AS. S is actually AS is actually the fin area plus A into unfin. Okay, yeah. So now here, so now we are actually going to have this. So therefore we can actually write as QT. QT can be actually written as, we are actually going to rearrange this. Okay, I'm just going to give the equation. So we are actually a bit of time. It is actually going to give us H into AT into 1 minus N into AS divided by AT, 1 minus eta F, okay, into theta. It is just simple algebra. Instead of A fin, we are actually giving it as A fin is actually written in terms of AT. Okay, A unfin. A unfin is actually written in terms of AT. AT and NAS. So if you are actually doing that, then you are actually going to get the relation. Okay. So we actually got a QT, but what is actually Q max? What do you think is actually Q max? Okay. What is actually Q max? For a fin efficiency, what did we actually say? Q max is actually the condition where the full fin is actually at the same temperature. So here, what we are actually saying is that the same thing, only that all the fins plus the unfin area is also at same temperature, the maximum temperature possible, which is at TB. Okay, yeah. So the here we can actually write that the Q max is equal to H into total area into theta B. So this actually gives us overall efficiency is equal to QT divided by Q max. This is equal to, these terms are actually going to get cancelled. Only in the bracket term will be actually remains 1 minus NAS divided by AT into 1 minus eta F. Okay, so that is actually the overall efficiency of the system. Okay, so that is actually the overall efficiency of the thing. Okay, so any doubts still here? Yeah. So now we actually understood this overall efficiency of the system also. So now we have to actually see now this overall effectiveness now. So what happens if you are actually going to have a multiple fins, and how this effectiveness comes into picture? Okay. Effectiveness for multiple fins. Effectiveness for multiple fins. Okay. So the same thing only means whatever we actually discussed, it is actually being extended to the multiple fins. That's it. Okay. So we actually saw that the Q total is equal to going to be Q from fins plus Q from unfin. Okay, so that we actually know. But again, we actually saw that Q total is equal to eta fin into uh, h into a surface into theta b plus h into a unfin into theta b. Okay, and also is actually going to be here. So now, what is actually the effectiveness? Effectiveness is equal to Q total with fin. Okay, so Q total, or we can actually simply write as QT. Okay, so QT with fin and QT with no fin. Okay, so QT with fin and QT with no fin. Okay. So no fin means it is actually going to be something we need to actually look into. Okay, so no fin means, so if you are actually going to have this multiple fins over here, multiple fins over here. So this is actually the AF, okay, and whatever the shaded area, okay, whatever the shaded area, so that is actually going to be A unfin. Okay, so that is actually going to be A unfin. But no fin means what? No fin means the wall surface area. So that is actually A no fin. Unfin means actually the surface area in which the fin is actually not attached, whereas no fin means when our fin is actually not attached at all. So that is actually the non-fin condition. Obviously, we can actually calculate it by adding to a unfin. We can actually calculate by the taking the cross-sectional area. If it is actually a constant cross-sectional area fin, then n into the cross-sectional area. Okay, so that actually gives us the total base area for the fins, and a unfin plus that it is actually going to give us the total area. Okay, so anyway, we are not going to that much detail. Only that this basic equation gives us h. Yeah, so we are just going to give it h into a into unfin plus eta fin into n into a fin into theta b divided by h a no fin into theta. Okay. As I said, no fin can be actually written in terms of a unfin plus n into the cross sectional area of the fin and okay, instead of a fin as. Okay. So that actually gives us an effectiveness. Here you can actually see some bit of calculations are actually required. More information is required, like what is actually the base area of the fin and all those things. Okay. Yeah. So that actually concludes this overall efficiency of the fin. Overall efficiency as well as what is actually the effectiveness if you are actually going to have multiple fins. Okay. So there is actually one more small topic left. In the 5 minutes we can actually stop this. Okay, so here what we are actually going to take about is actually the thermal resistance concept for fins. Thermal resistance concept for fins. Okay, thermal resistance concept for fin. In order to summarize whatever we just discussed, first we actually saw what is actually the efficiency of the fin. It is given as q fin divided by q fin max. So if the wall surface of the fin is actually at the same temperature. Okay. So then we actually said something about the corrected fin length. So instead of say for a convective heat transfer, we can actually convert it into adiabatic tip with an effective length. Then we actually saw what is actually the effectiveness, fin effectiveness. Okay. How much is actually the heat enhanced by the fin compared to if fin was actually not there. So it basically says us how much heat is actually transferred more so that when we actually attach the fin. So that is actually the basic fin effectiveness. Yeah, based on that, we actually said with some basic equation, especially for this for long fin, we actually said that it is actually better to have multiple fins of a very small thickness so that perimeter is actually going to be increased and it is actually going to be beneficial. Okay. So then we actually saw what is actually the proper length of a fin means. How much is actually the long fin, and what should be actually the optimum temperature or optimum length, so that we are actually going to get the maximum heat transfer. So after that, we actually talked about the overall efficiency and overall effectiveness if we are actually going to have the multiple fins. Okay. Yeah. So there is actually one more small topic, which is actually the resistance concept. In 5 minutes, we can actually see. So for a single fin as well as for multiple fins, we are actually seeing for single fin. Okay. So we can actually see that. Yeah, we can see that. First of all, what we are actually writing is efficiency of a fin is equal to Q fin by Q max. So that's what we are actually saying. So therefore, we can actually say that Q fin, as we said, efficiency of fin into H into A theta B. Okay, so this we are actually using all the time. So just keep that in mind, QF. From resistance analogy, we can actually see that from thermal resistance analogy, we know that R thermal resistance. What is actually the definition for R thermal? Is equal to R total into delta T, right? So R thermal resistance for a fin. So therefore, we can actually write RT for a fin. We can say RT for a fin is equal to theta B divided by Q fin, QF, right? So therefore, we can actually, what is actually QF? Theta F into HAS theta B divided by theta F into HAS into theta B is equal to 1 by theta F H into AS. Okay, so that is actually the thermal resistance for the fin. So if you are actually drawing this thermal resistance, this is actually the fin if you are actually saying. So here Q fin is actually going in over here. So this is actually where we are having TB, and this is where we are actually going to have T infinity. Okay, so this, if you are actually writing it as actually an resistance from TB to T infinity, we are actually going to have 1 by eta f H into AS. Okay, yeah. So through here, it is actually fin is actually going. Is that clear? Any doubts? Can you all hear me? Can you just confirm?
Yes, sir.
Yes, sir, we
Yes,
can
sir.
hear.
Yeah, yeah. So this is actually the thermal resistance for a fin. For a single fin, if you are actually having, this is actually the thermal resistance. Okay, yeah. For multiple fin, just 2 more minutes. For array of fins, the same methodology we are actually using. Okay. So we said that eta 0 is equal to Q total divided by H80 into theta B. So Q total means it is actually the total heat transfer, including the fin. So here, for a single fin, it is only through the fin we are actually talking about. But for an array of fins, we are actually also including the heat transfer from the unfin area also. Okay. So here, RT overall, we can actually say that theta B divided by uh, QT, okay, theta B divided by QT, okay, is equal to 1 by eta 0 into HAT. So that is actually the overall efficiency of the system. Okay, if you are actually having these multiple fins, so the base temperature is at a temperature TB, and this is actually at a temperature T infinity. So we can actually write it as a single resistance. We can actually write from TB to T infinity. Total heat transfer is actually QT, which is actually heat transferred through the Q fin and through Q unfin. Okay, including both these, we can actually write eta 0 into H into A into T. Okay. But we also know that Qt, okay, so Qt, we were also writing in terms separately also in terms of a Qfin and unfin, right? So that concept also we can actually use. So that is equal to, but also theta b by Qt, we can actually write as 1 by n into effectiveness of fin into h into a fin plus h into a unfin. Unfin. So it is kind of a two resistance in parallel. So or it is actually the two resistance in parallel. One is actually through the fin and one is through the unfin area. Okay? So through resistance in parallel. So here you can actually see it is actually going to be a summation like 1 by 1 by n uh, n eta f into h into as plus 1 by h into a into unfin. Okay. So these are actually the in series in parallel. So these are actually the resistance in parallel. So we know that 1 by r is equal to 1 by r. All those equations. Okay. So TB and T infinity, if you're actually having, so here it is actually going to be 1 by n eta f into h into as. So this resistance, it is going to be 1 by 1 by h into a into n. Okay, so that is actually the equation for this. Okay, yeah. So this is actually the if for an overall system, either we can actually go for the overall resistance, which is actually the 1 by, yeah, here you can actually see 1 by, this one is equal to 1 by n into eta infinity his plus 1 by h uniform like that. Okay, yeah, you can actually just do the algebra and it will be actually easy for you. So you can actually write it in both the terms, either as a parallel resistance or as the overall system also you can actually use. Okay. So this is actually how you can actually extend this resistance concept to the fins, because here fins are actually 1D steady state conditions without heat generation. So basically the thermosystem analogy also going to be applicable over here. Okay, yeah. So any doubts in this? So that actually concludes our discussion on fins. So I will actually send some tutorial questions maybe by today evening. So it actually includes the cylindrical as well as the fins. So you can actually discuss it on coming Thursday. Okay. So if you have any doubts, you just go through these slides and all, or not slides, go through the notes, whatever you have actually written. Go through the textbooks also. If you have any doubts at all from the fin point, we can actually discuss. Or then we will actually move to the next topic, which is actually the transient heat convection. Okay. Yeah. So any doubts? Yeah. Okay. Okay then. If possible, I will just send you this note, today's note at least, since the recording was actually not done. But I don't know how much you can actually get from this. But still, I will actually send this note. This is actually one note. So I think you have to install the OneNote, then you will be able to see this. Okay, okay, okay. Then, if you have any doubts, we can discuss. Otherwise, we can stop the class. Anything? Okay, okay. Then have a nice day to all.